In your video discussion assignments where you had to talk about what you found challenging from last week, a number of you mentioned that you had a hard time with word problems, so either word problems in general, just figuring out where to start and how to work through them, or just dealing with that dirty four-letter word called math. And so I'm going to go ahead and walk through question 4 from your bacterial growth worksheet. You can find the answer keys to these on Canvas, which kind of shows you the work, but sometimes it's nice to be able to listen to someone work through the logic of the problems also. So whenever you have word problems, it's beneficial if you indicate and kind of highlight in the problem the important information. As we're working through, we're going to read this problem that's telling us we're working in a hospital lab. We've got a urine sample to test for a UTI, and it's going to be diagnosed if there's 100,000 CFUs per mil or more. Now we're going to have to figure out the number of bacteria in the sample. So we're going to do a viable plate count, determine the CFUs per mil. To do that, we're going to take 1 ml of urine, add it to 9 ml of sterile saline, and then do a dilution series like what we see below. It tells us we plated 100 microliters. Remember, in the end, we're going to be calculating CFUs per milliliter. So if it tells you the amount you plated in microliters, you're going to need to convert it. And then it gives you the information from the plate counts. So let's draw those on here so that we can kind of have a better understanding of what it is that we're really looking at. So this would be tube 1, 2, 3, and 4. And as we read through the problem, it tells us when we plated from tube 2, when we plated from tube 2, we ended up with 350 microliters on the plate. When we plated from tube 3, we had 32 colonies. And when we plated from tube 4, we had 5 colonies on the plate. Remember, our magic countable range is between 30 and 300 CFUs per mil, which tells us this is going to be the one we want to use our calculations from. The equation itself, remember, with CFUs per mil, is going to be the number of colonies divided by the dilution times the amount plated. I know there was an error in the actual worksheet that had them added, but your denominator is multiplied. So to fill that out, we're also going to need to know what dilution this tube 3 is compared to the urine sample. For our dilutions, we've taken 1 ml and transferred it into 9 ml. So that's 1 ml in, with now a total volume of 10 milliliters, or a 1 to 10 dilution. Same thing in this tube, and this tube. So while the tube itself is a 1 to 10 dilution, we want to know how dilute it is going all the way back to the urine itself. To do that, we have to multiply all of those dilutions together. So 10 times 10 times 10 gives us an overall dilution of 1 to 1,000, which you can also write as 10 to the minus 3. And so that's the information we'll need now to fill out the actual equation down here where we want to solve for CFUs per mil. So we know that our number of colonies was 32, and that's going to be divided by the dilution, which we figured out was 10 to the minus 3, times the amount plated. Now remember, the amount plated, it was said, was 100 microliters. We're going to need to convert that to milliliters. Okay. When you look at microliters, they are the smaller unit compared to milliliters. Because they're a smaller unit, we're going to move the decimal to the left. And there's a unit of 3 between these, so microliters are 1,000 times smaller, which means we're going to move the decimal point 3 places, 1, 2, 3. So we'll have 0.1 milliliters. Remember, these were colonies. And so when we do that math, we're going to get a total of 320,000 CFUs per mil. B says, do we say the patient has a UTI? Yes, we did, because this is greater than the 100,000 limit that was what we needed to have as a UTI. And so that's how you work through these dilution problems. There is a way to do these with a slightly different formula, but I found just giving you guys the one formula tends to be a little bit easier for people. If you are curious about the other way to do it, you can send me an email and I can let you know what that is if you're really complicated by this one and you want to try it a different way. Okay, so now we're going to move on to the next problem. And this is just part C of the same problem. So we're still going to be using the information that we had to calculate above to finish the rest of this. So again, we've now got more information, so let's see what matters here. So we learned that the nurse who collected the sample didn't actually send it to the lab right away. Instead, it sat in the patient's room for 4 hours. The generation time it's giving us for E. coli at that temperature is 40 minutes. And we want to know how many cells were likely in the patient's sample when it was first collected. Because remember, if it's sitting at room temperature, those bacteria are going through binary fission, they're dividing and growing, and so after 4 hours, the number we calculated when we did that serial dilution above is not going to be the number that was actually in the urine when it came out of the patient. So we're going to have to use those couple different equations for exponential growth. And I'm going to walk through them to try to see if we can make it a little bit more straightforward in how we use these. So remember, the overall equation B equals big B times 2n. Now, in order for this to make any sense, we need to know what those variables mean. And sometimes it's actually even just easier to write the variables instead of the equation. So little b was the number of cells after growth. And that equals big B, which was the number of cells before growth, multiplied by 2 times the number of generations, which is what n is. But the other key is that most of the time the problem doesn't actually tell you the number of generations. Instead, it just tells you how long the cells have been growing for. So to solve for that n, to get this value, we actually need to use the other equation, which was that the generation time equals the total time of growth divided by the number of generations. When you rearrange that formula, you get the number of generations equals the total time, so the amount of time the cells were growing, divided by the generation time. Now, students tend to get fixed on looking at kind of formulas and forget what they're really doing. So if I had told you that you were going to have to meet with a different person every 30 minutes, and you're going to have to do that for 2 hours, and then I asked how many people you were going to have to meet with, pretty much everyone would go, oh, I'm going to meet with 4 people, because you took the 2 hours, you divided it by 30-minute intervals, and got 4. That's all you're doing for the number of generations. We're just saying over a set period of time, every 30 minutes, bacteria are doubling. If they grow for 2 hours, we would have had 4 generations. So that's really all this equation is looking at. And the other thing is, if you don't like using 2 equations, you can always take this number of generations and replace it with that. So we could have written this as 2 to the total time divided by the generation time. And then if you write the equation like that, you've got all the pieces, you just need to plug the numbers in for them. So if we come back up to the problem to see what our values are, we're trying to solve for the number of bacteria that was there when it was first collected. Okay, so remember, it's grown for 4 hours. So we're trying to solve for big B in this case, the number of cells before growth. We know our little b because our little b is what we solved for up here. Okay, we had this sample of urine. We determined there were 320,000 CFUs per mil into it. Turns out that was how much there was there after 4 hours of growth. So that's our number for the afterwards. So we can go ahead and start plugging numbers into this equation. So we know there was 320,000 and a cell's in there before. We're trying to solve for how many were there before the growth. And now we've got 2 times the total time, which was 4 hours. 4 times 60 minutes is 240 minutes. And it told us the generation time was 40 minutes. And then we start doing the math. So 240 divided by 40 is going to be 6. So this is saying 2 to the 6th times our x that we're solving for equals 320,000. And now we're going to need to say, okay, well, what value then is 2 to the 6th? If you do 2 to the 6th, that's going to be 64. And then we rearrange to get x all by itself. 32,000, or 320,000, sorry, divided by 64 is going to give us 5,000 CFUs per mil before the 4 hours of growth. And then the question asked, does that change your decision? And the answer is going to be yes. We no longer say there's a UTI, right? Because this is under the 100,000 CFUs per mil that needed to actually diagnose the urinary tract infection. So this also shows why it's so important that when you collect samples, they're either put in the refrigerator to stop growth or they're immediately sent to labs, because if the cells grow over time, you might get false positive results just because the bacteria were growing after they were already collected. So hopefully that helps with some of the math as you see kind of working through using the equations and how you pull the information out of the problem. If you're still kind of struggling, reach out to me. There are practice problems in the exam module under the exam study questions. Some of those have some practice problems in them. So go ahead and try them. And then if you want to check your answers, send me a quick email and I can let you know if you did them right or not. Good luck on the exam this weekend.